Okay, so we're going to do an example of beam connection or a bolted connection here. So we're going to calculate the design resistance of a bolted connection shown below. So this is a connection like that you would require for a flint truss member spliced within your project. So what have we got here? Oh, sorry, noise behind me. What have we got here? So we've got one plate, we've got another plate. The two plates are bolted together with these 8 bolts. Plates are bolted together, and the plates are being pulled apart. So in the direction of the plate, so one going up the way, the other plate going the other way. Things to watch out for. Well, there's 2 plates. One of them has a thickness of 12 millimeters thick. The other one has a thickness of 10 millimeters thick. They're both of grade S355 steel, so that's another thing to be careful of. That's the grade of the steel. Both S355 steel. We can see that there's 8 bolts, so that's 8 bolts. M20 is the type of bolt. It means 20 millimeters diameter. So M20. So what do we know from that? Well, M20, that tells us that the diameter of the bolt is equal to 20 millimeters. Grade 8.8 in there, so that tells us the grade of the bolt. So then we know that the Fy of the bolt is equal to 8 multiplied by 8 multiplied by 10, which is 640 newtons per millimeter squared. And we know that the ultimate strength of the bolt is equal to the first 8 multiplied by 100, which is equal to 800 newtons per millimeter squared. Okay, so I know that. Or I'll also get that from table 3.1 in Eurocode 3, part 1, part 8. Okay, so just a reminder that when I put that little 8, the superscript up there, that's EN1993, part 1, part 8. Okay, so that's the grade of steel. And also this other grade S355. So I need to go to table 3.1 as well. Table 3.1, I think, it's in the Eurocode 3.1 part 1, and that will tell me that we have the thickness is less than or equal to 40 millimeters, thickness of the plate. So that implies that Fy of the plate is equal to 355 newtons per millimeter squared, and then the ultimate strength of that plate is equal to, hopefully I have it right from the code, 470 newtons per millimeter squared. Okay, so that's a couple of things I've took note of already from the properties I'm given. So as I know the bolt diameter, D0. I also, what else do I know from this picture here? Take a different color. I also know that the diameter of the hole here, the hole diameter, D0, is equal to the bolt diameter plus 2 millimeters. Okay. Unless I have relatively large bolts, it's always the bolt diameter plus 2 millimeters. If it's a bigger bolt, it's the bolt diameter plus 3 millimeters. Okay, so this is the hole diameter. Okay, so here I have a 20 millimeter bolt, and I have a 2 millimeter clearance around the bolt. The bolt can get in there, so that's 22 millimeters. Okay, so I've got those worked out, and then I have the edge distance E1, pitch distance 90, edge distance E2 35, and the gauge distance P2 at 200. Okay, so I have a couple of the things that I need. So let's start doing the calculations. Okay, so first thing I can do is, well, I have the bolts. I know they're 20 millimeters, so I can get the area of the bolts from this. So I go to the blue book. I've just gone to the blue book. I've gone to page 308. Now the reason why I went to section D, okay, section D as grade S355. Okay, so S355 you can see there. So that's why I'm in section D. If it was a S275 plate, then I would go to section B. Okay, then the diameter of the bolt is 20 mil. Find out this instead. So it's a 20 mil diameter bolt. We said that we'll assume that the bolt is passing through the root area. So the area of the bolt is 245. And actually, in this table here, it's going to tell us if it's in single shear, which this one is. It's just one shear in it. Then we know that the bolt shear capacity is equal to, the shear capacity. So single shear, FVRD, is equal to 94.1. So I can read that straight out of the blue book. Okay, so from the blue book, effectively, page D303, FVRD equals 94.1 kilonewton per volt. Okay, so that's the first thing done. The shear connection done. But you can also look at the table. This is table. Sorry, I should put the table number. Table 3.4 here. So we have FVRD is equal to alpha FUB A times gamma M. So if we put all those values in, our grade of bolt is 8.8. So it's a grade 8.8 bolt. So that's AV is equal to 0.6. So there's 0.6 in there. The ultimate strength of the bolt, that's 8.8. So that's 800 newtons per millimeter squared. The cross-section area we get from the blue book, which is 245 millimeters squared. So put that in there, 245 millimeters squared. All divided by the material factor of safety, 1.25. And when we work that out, that implies FVRD is equal to 94.1 by 10 to the power 3 newtons. So FVRD is equal to 94.1 newtons. Okay, so that's the shear resistance of the bolts. So that's the first one checked, which is the shear resistance per plane. So number two, we're going to check is the bearing resistance. Okay, so we've checked the shear resistance per bolt, which is 94.1. There's a dot there. That's 94.1. Now we're going to check the bearing resistance. Okay. We get the bearing resistance of the bolts. It's going to be easier if I bring it with me. It's easier if I put it on each page so I don't have to be flicking back and over. Okay, so we're now checking the bearing resistance. So we've checked the shear resistance, we've worked out that 94.1 kilonewton per bolt. So every one of these bolts, all 8 bolts, each individual one has got 94.1. So the combination, the shear resistance of the whole lot of them, will be just 8 times that. Now I need to check the bearing. As I said in the lecture, the bearing resistance is going to check for if we put in alpha B as equal to 1, then that means that we're checking for plate bearing. If we put alpha B equals to this, we're checking for bolt bearing, and if we put it equal to alpha B, we're checking for in bearing. So in this calculation here, in this equation from table 3.4, we're checking for in bearing, bolt bearing, and plate bearing all together. So let's do those checks. We're going to have to do them for each row of bolts. Okay, so each row of bolts, we're going to have to check which one is in there. So first thing to note is, well, we have one plate is 10 millimeters, the next plate is 12 millimeters. So the one that's going to be the more critical is the thinner plate, the 10 millimeter one. So we don't even need to check for the 12 because the load has to pass through the 10 millimeter into the bolt here, then into the other side of the bolt, and then back into the 12 millimeter one. So if the 10 millimeter plate itself or the bearing against the bolt isn't strong enough, there's less bearing in this in the 10 millimeter than there is in the 12 because it's a thinner plate. So therefore, the 10 millimeter is always going to be the critical one. So we don't even need to worry about the 12. So I suppose that's the first point to note here. So 10 millimeter thick plate will govern. So that's the first thing to note. Okay, so then we'll put the rows of bolts. So 10 millimeter one is the one in the back. Okay, so this is row 1 down here. Row 2, row 3, row 4. Okay, so we've got 4 rows of bolts in there. So if we're going to check the first row, to check each one individually, so we check the first row. So we know that the bolt resistance is equal to K1 times alpha B FU D times T all over gamma M2. Okay. We have that there from up in that table above, table 3.4, Eurocode 3, part 1, part 8. Okay, so then the first thing we're going to work out, I suppose, so it's an edge bolt. So this is an edge bolt. Okay, so it's an edge bolt because we can see when we pull the plate up the way, so we're going to pull this plate up the way, we can see it's near the edge. So that's the first bolts, that's our first pair of bolts, our first row of bolts, sorry, that's closest to the edge. So it's an edge bolt, so therefore we need to use the formulas associated with an edge bolt in there. Okay, so we have for an edge bolt, so that implies K1 equals smallest of, so it's the minimum of 2.8 E2 divided by D0 minus 1.7 or 2.5. So that's equal to the minimum of 2.8. No, don't take my hand. E2 is equal to 30, or sorry, is it 55? That down there, yeah, that's 55 on that thing. So times 55 all over D0, which we said D0 was the bolt diameter plus 2 millimeters, divided by 22, minus 1.7 or 2.5. So that's equal to the minimum of 5.3 or 2.5. So K1 is equal to 2.5. Yes, that's for row 1. Then we need to check, so that's that one. Then we're also going to check for in bolts. So alpha D, and alpha D is equal to E1 divided by 3 times D0. Yeah, okay, 3 times D0. And E1, from the figure over there on the right hand side, we can see E1 is 35 millimeters. That's the edge distance in the direction of loading, 3 times 22. And that's equal to 0.53. Okay, so we have 0.53 in there. Then we have alpha B is equal to the minimum of alpha D FU B all over FU, or 1. So it's going to be the minimum of those 3. So that's equal to the minimum of 0.53. Alpha UB, so it's the strength of the bolt, divided by the plate. That's divided by 470, or 1. So alpha B is equal to the minimum of 0.53. And then this is going to be greater than 1. So, sorry, I can rub out that, so because I can see that straight away. That's 800 divided by 470 is greater than 1. I have 1 at the end, so 0.53 is the one that's going to govern. Alpha B is 0.53. So, some questions here. Where did you get the 2 millimeters from in D0? So that comes from one of the clauses in the code. It tells us that the hole diameter is always 2 millimeters bigger than the bolt diameter, unless we have larger bolts, and then we make 3 millimeters bigger. Because you have to have a bit of tolerance so that you can fit the bolt in. So if you made the bolt hole on the plate the exact same as the bolt, the chances are it won't fit through because everything doesn't line up perfectly. So you allow 2 millimeters in there. Can you go back for a second? Okay, so can I go back to 1 before? Page? Ocean, or is it back further? Where do you want me to go back to? Okay, so just recap on what we've done. Because of the plate thickness is the very first slide, this one. Okay, so the plate thickness is less than 40 millimeters. We know from going to table 3.1 in Eurocode 3, part 1, that if we look at the thickness of plate less than 40 millimeters, we have a grade S355, then we have Fy is 355 newtons per millimeter squared, and the ultimate strength is 470. And because it's a grade 8.8 bolt, we know that the yield strength of the bolt is 640 newtons per millimeter squared. The ultimate strength is 800 newtons per millimeter squared. We know the bolt diameter D is equal to 20 millimeters because we've got that, we've been given that in the question. Therefore, the hole diameter is 20 millimeters plus 2, which is 22 millimeters. Okay. Then we went to the blue book to find out, well, if we have a 20 millimeter bolt diameter, what is the cross-section area? So we use a tensile stress area if the bolt root is in where the hole is. So that's 245 millimeters squared. But also from that table, from the blue book, looking at grade S355 steel, we can get the shear strength straight from that table, which is 94.1 kilonewtons. And then that was a shear strength done. We can also work out that shear strength using the equation there, which is alpha V FUB A times gamma M1, 0.6 for the factor, and based on grade 8.8 bolts, 800 newtons per millimeter squared, because that's the bolt ultimate strength, 245 millimeters squared, which is the cross-section area that we got from the blue book, divided by 1.25, which is the material factor of safety. And that should give us the same thing. Now we're on to bearing resistance. And so what we did is we're on the first row of bolts, which is at the very bottom there, so one the closest to the edge on a 10 millimeter thick plate. We're using the equation for bearing resistance from table 3.4 in Eurocode 3, part 1, part 8. As it's an edge bolt, then the K1 value is equal to the smallest of 2.8 E2 divided by D0 minus 1.7 or 2.5. So we put those into the equation there, and we got out that the minimum value is actually 2.5. So that's K1. And then alpha D for an edge bolt is equal to E1 divided by D0 for this edge bolt. And we put E1, which is 35, which is from the diagram here that we're given. D0 is 22, and then we get 0.5 at 3 back out of it. So that's alpha B is a minimum of alpha D, FU E over FU, and divide and 1. And then we know that the ultimate strength of the bolt is 800, the ultimate strength of the plate is 470. That's greater than 1, and 1 is greater than 0.53. So that's alpha B is 0.53. Now we have K1, we have alpha B, we have FU, and we have D times T. So that will allow us to work that out. So we can do that. So we're still on the first row of bolts. So the bolt resistance is equal to K1 alpha and B FU DT times gamma M2. So we worked out those earlier on. So that was 2.5 for K1, 0.53 for alpha B, FU, which is the strength of the plate material, 470 newtons per millimeter squared, and the bolt diameter is 20 millimeters. Thickness of the plate is the thinner of the two of them that we're looking at, 10 millimeters. That gives us newtons on the top, which is what we want because it's the force that we're looking for. So we know that we have the right stuff in there, and that's 99.6 by 10 to the power 3 newtons, which is 99.6 newtons. Okay, so that's row 1. So that's the first row done, row 1 on the bottom. Now we're going to look at the other rows, row 2, row 3, and row 4 are all the same because they're all internal bolts. Okay, this row 4 is an external bolt when you're talking about plate, the 12mm thick plate. It's an internal bolt when you're talking about the 10mm because there's a lot more material up here. We've just cut it off. So 2, 3, and 4 are all the same. Okay, so we're going to look at row 2 to 4. Basically, they're internal bolts. Okay, so internal bolts. So K1 value. So what's K1 value? So K1 for an internal bolt here. So it's the smallest 1.4 P2 D naught minus 1. That's the minimum of 1.4 P2 D naught minus 1.7, 2.5. Okay, so that's equal to the minimum of 1.4 times P2. So P2 is the gauge length, so it's 200 there. Divided by D naught is 22. And minus 1.7. Minus 1.7. And then 2.5. Okay. Okay, so we put that in, we get K1 is equal to 2.5. Okay, and then it's an inner bolt, so that's the inner bolts that we're doing. Okay, so we've done that one for the inner bolt, and then it's an inner bolt up here, so we need to use this one for alpha D. Okay, so alpha D is equal to P1 over 3 times D naught minus a quarter. Okay, which equals P1, so we have P1 there, which is 90mm, 3 times 22 minus a quarter, and that's equal to 1.11. It's 1.11, okay? So alpha B is equal to the minimum, alpha D times FU B all over FU and 1. So that's equal to the minimum of 1.11. And we said that's 800 all over 470 and 1. That's just equal to 1. That implies that F BRD is equal to K1 alpha B times FU DT all over gamma M2. And so we put those into the formula, so that's 2.5. Alpha B is equal to 1. 470. D is 20. And T is 10. All divided by 1.25. Yeah. Oh yeah, there you go. All divided by 1.25. And that's going to give us 188 by 10 to the power 3 newtons, which is 188 kilonewtons. Okay, and then from above, FVRD is equal to 94 kilonewtons, which is less than or equal to FVRD minimum. So the minimum value of the bearing resistance that we've worked out is 99.6 kilonewtons. So that implies that F of the joint resistance is equal to NB times F V or D, which is equal to how many balls there? 8 balls times 24 kilonewtons. is equal to 752 kilonewtons. Okay, so that's the overall resistance of the joint, 572 kilonewtons, 772 kilonewtons. And then we need to check for a line joint. The line joint, so LF, length of the joint, in this case is 340 millimeters, isn't it? It's 340 millimeters. Then that's greater than 15 times the bolt diameter, which is 15 times 20, 5, which is equal to 300 millimeters. So then that implies it's a long joint. And then if you go back to the equation afterwards, you'll actually find out that the long joint you put in is 0.99. So that implies that the joint resistance is equal to that times NB times FV or D, which is equal to 0.99 times the resistance that we had, which is 752 kilonewtons, which is approximately equal to, say, 750 kilonewtons. Okay, so that's the first example done. That's the first example done. So the rest of them are going to follow a similar suit. It'll get a little bit more complicated when we have some other things within it, but that's basically a bolted connection design. So that's a bolted connection design, and you will need that for your project. You need to be able to design that for your project. To be able to do that. So what we're going to do, as I said, next Friday is we're going to do next Friday. Go get your jacket. Go get your jacket. What we're going to do next Friday is we're going to start the project in there, and then in the lectures then what I'll be doing is I'll be following up with more complicated connection designs and so on that we will need in the project later on. Okay, so has anyone any questions on that?